Tell us
Nandini.
about.
Okay. Same here, Nandini. I like being with all of you. It is very nice to,
And you are so sweet.
thank you, Bachi.
Oh,
Thank you
on
very
your
much.
video
It's
also.
very,
Ma'am,
You
we
are the
want to see
best.
your face.
Yes, ma'am. We love you.
so nice of you. So nice of you.
Ma'am, open your camera also. We want to see your face.
Oh, no.
Please, ma'am.
Yes,
Okay.
ma'am. Please. Song
No,
है
no, no, no.
हुक्का वाला.
Okay. See, not today, not today. I'll tell you, I'll tell you. So one day we will, reserve some time, and I'm sure that many of you must also be very talented. And so we will have a little, time. We'll set apart a little time where we can all, contribute. We can sing together because it's such an unfortunate time that we've not even been able to see each other once. So I think that day we can all, get ready, dress up, and stream our cameras and put our little performances together. So there is no stopping us. I think, we should be doing this one day. Okay. So we will fix up some time. Okay. Just remind me, and then we will do this. Right. Okay. And
Yes, ma'am,
now,
definitely.
okay. So happy Lodi to everybody once again. And
Same to you,
Same
ma'am.
to you,
Same
ma'am.
to you.
Same to you,
Same
thank
to
you,
you,
ma'am.
ma'am.
Bachu. Thank
Same to you,
you.
ma'am.
Thank you.
Same to you,
Thank
ma'am.
you. I can feel so much of, love and good vibes coming through, even though we have not physically connected with each other. So that's very nice. And with these words, let me start the next chapter, lesson number 3. Okay. Please let.
Ma'am, please sing the song.
Oh, okay. Okay.
Yes, ma'am, please.
हुक्का वाला. हुक्का हुक्का.
Okay, okay. So the traditional Lodi song is सुंदर मुंदरिए हो तेरा कौन बेचारा हो दुल्ला पट्टी वाला दुल्ले दी वे आई शेर शक्कर पाई. Then I don't remember. I just remember this much. And as I was telling you, so if kids, in it is customary for the kids to ask for little gifts from the elders on Lodi. So when they ask for gifts, and if the elders don't respond, then they would sing hukka be hukka ekar pukha, hukka be hukka ekar pukha. And if they take too much time, show some attitude giving you the gift, then you could sing ਸਾਡੇ ਪੈਰਾਂ ਹੇਠ ਸਲਾਈਆਂ ਅਸੀਂ ਕਿਹੜੇ ਵੇਲੇ ਦੀਆਂ ਆਈਆਂ ਸਾਡੇ ਪੈਰਾਂ ਹੇਠ ਸਲਾਈਆਂ ਅਸੀਂ ਕਿਹੜੇ ਵੇਲੇ ਦੀਆਂ ਆਈਆਂ. Okay. So that's it.
Ma'am,
Right.
your voice is so sweet.
Oh, thank you.
Ma'am, it's beautiful.
Thank you. Yeah, sorry, come again, beta. Come again.
Ma'am, it's beautiful. Your voice is so sweet.
Okay, okay, okay. Thank you so much, Sulekha. This was Sulekha, right? Thank you, Bache.
Yes, ma'am.
So, I'm
And
sure.
you are our favorite teacher.
Oh, thank you so much. Thank you, Lynette. So nice of you. I love you too. I love you all as well.
We love you, ma'am.
Thank you, Bache. Thank you so much. It's very great to hear such words. They encourage me, and uh, you know uh, they give me a lot of warmth in these cold days. So I'll keep these compliments rather, that you're giving me, showering me so generously with. I'll store them with me, and whenever I'm a little down, I'm sure I'll look at them. Okay? God bless you all. God bless you all.
Thank you,
Correct.
ma'am.
Yeah, Sejal, thanks. Thanks, Garima. Yeah, so nice of you all. Such a nice lot of students.
Ma'am, there
Very
is a comfort zone with you.
okay, okay, right. Thank you. This is very necessary. This is very necessary because I'm not just here to teach you computer system architecture, but you can obviously share your problems as well, as and when you like. Okay, so yeah, thanks, Ching. So nice of you. Thank you, Anu, Nandini, Lynette, Ishika, Astha, Nikita, Nisha Pandey, Disha Vadva, Param, Shweta Chaudhary, Gauri. I hope I don't miss out on any name, but I'm just sliding through. Chainika, Kirti, Astha, Dipali Nayak. So I can safely say that it's been a very nice Lodi for me as well now. Ragini, okay, so Shivani, Vanshika Jain. I hope I've not missed out on anybody's name. Okay, so thank you all. And let us now start with our next chapter. Okay, we need to get going. Right. Sejal, Priyanka, Tashu. Right. Okay. So let us start with architecture now. Okay. So we are going to start with lesson number 3 now. Nitisha Verma, Soumya Gupta. Thank you, bache. Thank you. Okay. So, yeah, Anjali, thank you to you too. And let me start the presentation now. Okay, let me know when my screen is visible, right? So we are going to be starting with data representation, chapter number 3, data representation today. The first thing that we are going to discuss is uh, number systems. Okay, I already gave you a very broad introduction to the number systems earlier, right? I'll go over it again. Let me know when my screen is visible to you.
Ma'am, it's visible.
Okay, good. So this portion, students, you'll find is uh, this is more computation oriented, material, and this part is therefore also very, scoreable. So sometimes you get a numerical or two, 2 marks, 4 marks, 6 marks. So 2 or 3 parts to convert from one base to another. Okay, conversions, number system conversions. So that is what you can expect in the examinations. Okay, so please see, as I told you, that we that is the human beings, we do our normal maths and we, deal with numbers uh, which are, you know, 10 in number, start from 0, go up till 9. Now, every other number is just a manifestation of these basic 10 digits, right? So, let me talk about 10, for instance. It is formed by the combination of 1 followed by a 0. Similarly, let's say 11, 1 followed by a 1, and so on and so forth. I think I, you know, did this combination permutation and showed it to you on a slide one day, that to these basic 10 digits, that is 0 to 9, when we first we attach 1, so we get numbers from 10 to 19, then 2, then we get from 21 to 29, 3, 30 to 39, and so on and so forth. And then again, we start adding numbers from 1, 2, 3, again in this order, to get the 3-digit numbers and then 4-digit numbers. So every other number in our world, so as to say, is actually a manifestation of the basic 10 digits. Now, since a 10 is known as a deca, therefore, this number system that we use in our normal lives is also known as the decimal number system, right? So, since our number system has 10 basic digits, so therefore we say that our the base of decimal number system, or its radix, which is the other word for base only, is 10, right? We are already now familiar with the binary number system as well, which we know contains only two digits, namely 0 and 1, and therefore the name bi and binary, right? Obviously, only two digits, so the base here is 2, right? Now, there are other number systems as well that we have formulated. For instance, you can see two number systems on the screen right now. The first one is octal and the other one is hexadecimal. Now, octa stands for 8, so the base is 8, and therefore we start the numbers from 0 and we pick up the first 8 digits in this number system, right? So the next number in this series for the octal number system would become 1, 0, right? So 0 till 8 are represented by 0 to 7. How will 9 be represented? It will be represented by a 1, 0. Then 10 will be represented by a 1, 1, and so on and so forth, right? So this is the similar way of forming the next numbers after the basic digits as we do in the decimal number system for all other number systems, right? Then yet another number system that you see on your screen is hexadecimal. Okay, hexa stands for 6, decimal stands for 10. 6 plus 10 is equal to 16. So the base of this number system is 16, and the first 10 digits or symbols for this number system we can borrow from our decimal number system, that is 0 to 9. But then what do I do? Where do I get the remaining 6 symbols from? So we borrow them from the alphabets. We borrow the alphabets A to F to represent the numbers 10, 11, 12, 13, and 14 and 15 respectively. So A represents 10, B 11, and so on and so forth till F, which represents 15. Okay, so these are the basic number systems. There are definitely, other number systems. Some of them may be named, some of them may not be named, but We can think about, a number system, for example, which has a base 5. As soon as I say that it has base 5, whether I give you its name or not, you should be able to understand that it will have only 5 digits. So, what digits will that be? We always start from 0. So, 0 to
4.
4. Yes. Right? Another number system is duodecimal. Okay, so duodecimal means duo means 2, decimal means 10. 2 plus 10 is equal to 12. So 0 to 9, and then two digits A and B. So any number system uh, can be thought of as long as we have its radix. And you will see that most of the conversions that we are going to be talking about today, the manner or the basic algorithm, the basic way, that is to change from one number system to another, will remain the same. We will assume that we are talking about a particular radix, let's say R, okay, and generalize our method, and then see how they apply to each of these number systems when we are converting from one of them to another. Okay, so but there is a question that comes to my mind. Why have all this? Why introduce all this complexity in our lives? We're happy with the decimal number system. We've learned them from nursery. We start learning them from nursery, and then why invent so many number systems and then devise methods to convert from one number system to another? Why do so? Anybody would like to, you know, think about it and let me know?
Can I tell?
Yes. Please speak up your name first. I can't see your names now because
Ma'am,
I'm looking at the
Chenika.
presentation. Yeah.
Chenika.
Chenika, yeah.
Ma'am, actually, suppose if we take binary number system, and suppose we have a big number, suppose we have something like 10,600 something. So when we try to represent that number in binary, the amount of space it takes up is huge. The number in zeros and ones will be huge. But in that place, if we try hexadecimal, it becomes lesser, or octadecimal, like it becomes lesser and lesser. If the higher the base is, like this radix is, the lesser number of digits we need to represent that particular value. So that's why we create these systems, so that we don't take up too much space to represent a particular number. Am I
Exactly.
right?
Exactly. Yes. Very good. That's exactly the point. So we already know why we had to work with the binary number systems, right? We already have that motivation. So we had said that inside a computer system, we can only use the uh, bits and bytes. So only two numbers, zeros and ones. We have to play only with them, right? So that's okay. In our normal life, we use decimal number system, and for system we use binary number system. But then why all these other number systems was my question. So for example, the octa, hexadecimal, as you see on the screen, and I've talked about duodecimal and other bases. So why to resort to these number systems? See, when we are working with the bits, that is zeros, ones, it's it's very cumbersome sometimes, to write so many large numbers of zeros and ones, and then remember them and put them correctly. Even when typing zeros and ones, even when we are typing zeros and ones, we inadvertently we make some mistake. So please think of yourself typing a complete page which is filled with nothing but zeros and ones. How many mistakes would you make? Is there anybody who thinks he will not even make a single mistake? In fact, we will be making many mistakes, right? We will be making many mistakes. So, for easy representation, okay, we choose a more compact way of representing the binary digits, that is the bits, and octal and hexadecimal numbers come in handy there. Okay, so it becomes a very compact representation. Okay, uh, what do I mean by this? We will see when we convert from binary to octal, binary to hexadecimal, and vice versa. That is, from octal back to binary and hexadecimal back to binary. So you will yourself realize that, what do we mean by this. Okay. So for the time being, let us start. So what are we going to see now? We are going to see next how to convert from one of these number systems into the other number systems. Okay, these are the types of conversions that we are going to be looking at. So the first conversion that we are going to be looking at is base R to decimal. Okay, so from binary, for example, from binary to decimal, octal to decimal, hexadecimal to decimal, okay, and then the vice versa, decimal to all these bases. So decimal to binary, decimal to octal, decimal to hexa. This is going to be the first set of conversions that we are going to look at. Then we are going to look at binary to octal, binary to hex, and vice versa. So octal to binary, hex to binary, and then the interconversion of octal to hexa and hexa to octal in between themselves. Okay, we are going to be focusing on these four number systems. But as I said, suppose you get a question on any base R, you should be able to answer it, because the basic way to change from decimal to any base R will remain same, and vice versa it will remain same. So for all these types of conversions, we are going to first look at a general way of conversion, and then proceed likewise, right? Okay, so the first conversion that we are going to see is base R to decimal. How to convert any number into decimal number system. So for that, you know, I've just written a number in the decimal number itself. Okay, just to remind you what this means. So suppose this is a number 724.5 in decimal number itself. How do we denote this is decimal? We just put its base here. When I've written a number like this here and put 2 here, it means it is binary. This means this is 8, means this is octal, and this is
Hexadecimal.
hex.
Hexadecimal.
Hex, right? So the base which we put here tells us the number system that we are using. Okay. So this number in decimal number system, in any case, if you remember, how does it become 724.5? If you remember, each of these positions has a corresponding weight attached with them. What is this weight? You remember you used to do something, some small questions like in your smaller classes, like what is the face value of this number and what is the place value of this number, right? So this is ones, tens, hundreds, thousands. Do you remember? So what is
Yes,
the
ma'am.
face value of these numbers is obviously 4
Yes,
to
ma'am.
7, but their place value is, for 4 it is 4, 2 it is 20, 7
20.
it is
700.
700. And how do
700.
we get that? How do we get that? So for ones, this is 0, 1. For this it is 1, and for this is 2. So if I when I multiply 7 with 10 raised to the power of 2, 2 with 10 raised to the power of 1 and 4 with 10 raised to the power of 0, then we get it 724. Is that right?
Yes,
Yes,
Yes
ma'am.
or
ma'am.
no?
Yes,
And
ma'am.
5 is multiplied by what? It is multiplied by 10 raised to the power of minus 1, right? So we get 5 by 10, which gives me 1 by 2, which is equal to 0.5. This is how we used to do it, right? This is how our numbers are, how they are. That is, a 724 becomes a
Ma'am,
724.
you are not audible.
She is audible, Nandini.
Yes, ma'am.
Yeah,
You are
am I
audible.
audible?
Yes,
Yes,
ma'am.
ma'am. You are
Yes,
audible.
ma'am. You're audible.
Okay,
Yes,
okay.
ma'am.
Nandini, you can check at your end maybe. Okay, so similarly, it's very easy how to convert a number from any base to decimal. What we do is just this same thing. Okay, so we just attach these weights. So we multiply each number with this base that it is in. For binary, we will multiply by 2. For octal, we will multiply by 8. For hex, we will multiply by 16. So let's say 1, 1, 1. Then I attach the normal weights as we are used to attaching. So if there was a point here, then on the right hand side, I would have attached minus 1, minus 2, and so on and so forth. On the left hand side, I will attach 0, 1, 2, and so on and so forth, and multiply each digit, whatever that digit is, with that number raised to the power of its weight. Okay, so what do we get? 1 into 2 raised to the power of 2 plus 1 into 2 raised to the power of 1 plus this 1 into 2 raised to the power of 2. Is this clear? Right? Yes or no?
Yes,
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 ma'am.
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 Yes,
Yes,
What will
ma'am.
we get?
Yes, ma'am.
4 plus, what will we get? 4
7
plus 2
2,
plus
plus 1,
1 is equal
7.
to 7.
7.
So now
7.
you know why triple one is equal to 7. You remember?
Yes,
I
ma'am.
told you to almost, memorize these combinations, right? So let us do it for something else now. Let us do it for 101. What is 101 in binary? What is 101 of binary in decimal?
I'm 5.
5.
5.
So today let us see how it becomes 5. Okay. So the first one that you see here, this one is multiplied by 2 raised to the power of 2. Then 0 is multiplied by 2 raised to the power of 1. Then 1 is multiplied by this. So I get 4 plus 0 plus 1 is equal to 5. Any problem?
No, ma'am.
No.
Ma'am.
No,
No,
ma'am.
ma'am.
No, ma'am.
Good, good. So this is another example. So please look at this example and let me know if there is a problem. Similarly, we are multiplying. Is the screen visible to you?
Yes, ma'am.
Yes, ma'am.
Is the second example clear as well?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes,
What is
ma'am.
the answer that we will get?
Ma'am, 19.
31.
19.
Yeah.
19.
What is 2 raised to the power of 4? It is 16, right?
16.
16 plus
Yeah, ma'am,
0
it's 19.
plus 0, 16 plus 2,
2. 2.
13
1.
plus 1,
1.
which is equal
1.
to 9.
19.
19.
19.
Right? Now, let us see how to convert an octal number to decimal. So, again, the same procedure. 7 into 8 raised to the power of
2.
2.
2.
2.
3 plus 3 into 8 raised to the power of
1.
1.
1.
plus 6 into 8 raised to the power of
0.
0.
Zero.
plus 4 into 8 raised to the power of
Minus
Minus
1.
1.
Minus one.
exactly right. Now let us we do this computation, and what do we get? We get it equal to 400. We just solve this and we get it equal to this number 478.5. Any problem?
No,
No,
ma'am.
ma'am.
No, ma'am.
No,
So
ma'am.
similarly for hex, please see. So F3, F is what? Please see. This is F means
15.
15, right? So we will substitute this value later. So it will be F into 16 raised to the power of 1 plus 3 into 16 raised to the power of 0, which is 1. Is this clear? This much is clear,
Yes, ma'am. Yes.
right?
Yes.
Yes, yes, ma'am.
So we substitute the value of F is equal to 15, and what we get is this. We solve and this is what we get. Is this clear to everybody?
Yes,
Yes, ma'am.
ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes,
Up
ma'am.
to now, any problem?
No, ma'am.
No,
Right,
ma'am.
right. Let us see another, one more example of each of these conversions. So actually, I want you to work them yourselves. Will you please do it?
Yes,
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 ma'am.
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 Yes, ma'am.
Okay, don't look at the
Yes,
answer
ma'am.
and do it yourself.
Done, ma'am.
Done, ma'am.
What? Okay.
Done, ma'am.
Okay, what are
Done,
you
ma'am.
getting? What are you getting?
I'm
19.
19.
19.
19.
Yeah,
19.
yeah, yeah. So I shortchanged you. Uh, I have given you the exact same numerical that we did on the last page, right? So, yes. Anybody who was not able to do it? Anybody who was not able to do it? Okay. So let us do the octal to decimal conversion now. Now this is a different example. 2605 of octal. Let us see what you get. 2605 of octal to decimal.
Done, ma'am.
Who is this?
Done, ma'am.
Done,
1408.
ma'am.
Huh? Sorry.
Ma'am, 1413.
Yes, ma'am.
1413.
1413.
413.
13.
Yes,
Okay.
ma'am. 1413.
Okay.
Yes, ma'am. 1413.
Yeah. Let us see here. So yes. Uh, since 8 raised to the power of 0 is 1, 8 raised to the power of you may just remember these small up till 2 3 power. You may just remember 8 raised to the power of 2 is 64. We generally remember 8 raised to the power of 3 is 5 and 2, and then we directly multiply 5 into 1, right? So 5 into 1 plus 0 is into 8, right? plus 6 into 8 raised to the power of 2, which is 64, plus 2 into 8 raised to the power of 3, which is 512, right? So this is equal to 1024 plus 384 plus 0 plus 5, which gives me 1413. Any problem?
No,
No,
ma'am.
ma'am.
No, ma'am.
No.
Good. Let us see another example. Now we are going to see from hex to decimal, right? So convert AC0 from hex to decimal. AC0.
Done, ma'am.
Done, ma'am.
Done,
Speak up
ma'am.
your names. Speak up your names
Ma'am,
with your.
answer done.
Ma'am,
Ma'am, answer
Akshaya
is done.
Khandel,
Ma'am,
well done.
Sreka Bansal done.
Ma'am,
Okay, good.
Ishita.
Akshita done.
Okay,
Ma'am, Sreka
what's
Bansal
your
done.
answer?
Ma'am, 2752.
2752.
Good. Excellent. Excellent. So this is how we do it. So A into 256, A into 16 raised to the power of 2, which is 256, right? Means 10 into 256 gives me 2560, plus C into 16 raised to the power of 1 is equal to C is 12, A is 10, B is 11, C is 12. So 12 into 16, which gives me 192, plus 0. 0 into 16 raised to the power of 0, which is 1, gives me 0. So eventually I add these three intermediate totals to give me 2752. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Any problem?
Yes, ma'am.
No, ma'am.
No, ma'am.
Right. So we have seen the conversion from base R to decimal today, and tomorrow we are going to look at the other conversions, that is the reverse conversion from decimal to base, then binary to octal, binary to hex, the reverse computations, and then octal to hex and vice versa. Okay, so we will do this in the next class. I will send you the link uh, for attendance now. Please mark your attendance. Any problem, anybody else?
No, ma'am.
Right, okay.
No, ma'am.